Hello and welcome to lecture 4. Today we're going to talk about linear time-invariant systems. And this particular class of systems is going to be extremely important for us, right? They show up everywhere, and the ability to model them, analyze them, okay, and have a deep understanding of linear time-invariant systems is going to be extremely important for all engineers. Okay, so we're going to focus on sections 2.1 through 2.2 of your textbook today. So let's get going. First of all, a quick recap of where we've been in the past few lectures. We have talked about a basic set of signals, right? We've talked about the unit step function. It's kind of like turning on a switch. We've talked about the impulse function, right? This is like a knock on the head, sort of, right? A very intense but very narrow signal, right? It goes to infinity at time t equals t, and it's 0 everywhere else. But it has a finite area. So the impulse function only makes sense, okay, when you consider the integral of this function, because the integral is still finite, not infinite. Even though the delta function goes to infinity at that point, right, at this time t, the integral under this is still finite. And this function is extremely important for sifting or taking snapshots of other signals. Now, we also talked about the exponential signal. This signal will appear a lot, okay, and for a good reason, right? A lot of the parts of our systems are things like capacitors and inductors, right? And the response of these kinds of components is exponential in nature. For that simple reason, the exponential function will appear often. Of course, there are more reasons for exponentials to appear often, but that's one of the simplest, most understandable of reasons. Now, we can take these basic building blocks like the step, okay, and derive other building blocks from it. For example, by simply integrating, right, a unit step function, okay, oh sorry, let me write u of tau d tau. If I integrate from 0 to t, right, I get the ramp function, right? The ramp function is kind of like an airplane taking off, right? And this is also a basic building block, but it's related to the unit step function. Now, another thing is that the delta function can be derived from the unit step function by differentiating it, right? The unit step function is essentially going like this. The derivative at this point is infinity, right? So the delta function is actually can be thought of as the derivative of the unit step function. So we've been using some basic signal transformations. For example, if we write delta of t minus capital T, it means that the delta function is shifted from 0, okay, to this point capital T, right? So this is the time shift of a signal. We can also scale a signal by multiplying it by something, okay? And we can add signals, we can subtract signals, okay? So these are some of the basic operations, that we can conduct on signals. And by using these operations and the basic building blocks, we can build up more complicated signals. As the simplest example, right, the rectangle function can be built up by essentially taking a unit step function like this and then subtracting out a unit step function like this, right? So if I subtract this from this, I get that, right? So these functions can be combined in a multitude of ways to give other signals that can be useful, right? Now let's today focus on this notion of a system, right? So a system, as we have discussed before, right, can be pictured as a black box, right? And we want to understand ways to mathematically understand or mathematically model a system. So a system has an input, okay, and we write that as x of t. This is a signal, and it has an output, which we write as y of t, which is also a signal, right? So we want to understand how to express this mathematically so that given this and this, we can figure out what this is, okay? That's known as the forward problem. Now, sometimes we're interested in the reverse problem, right? So we know what this is, knowing this, but we need to figure out what this is. That's sometimes possible. That's called inversion. Okay? So a variety of problems appear in the context of systems. Okay? And we'll talk more about them as we go. Right? Now, a system in general can be quite complicated or extremely simple. Right? We will start with simple ones, and then we will sort of, look at more and more complicated signals as we go. Now, a lot of signals have a very, very convenient property, right? So if I were to scale up x of t by a number c, a constant, so I take c times x of t, then what that means is that the output is also correspondingly scaled. You get c times y of t, right? If this happens, this system is said to have the scaling property. Okay, it's kind of like a proportionality, right? So you double this, this will double. You triple this guy will triple, right? Now, there are a lot of systems with this property, and the simplest of them is a case where y of t is simply the derivative, right? d by dt of x of t. When that happens, right? So if I have like what is d by dt of 2 times x of t, if you ask that question, right, then that's given by, this constant 2 can be taken outside, so it's 2 times d by dt of x of t, okay, which is basically 2 times y of t. So this simple system here, okay, is actually endowed with this nice property of scaling. Now, there are many systems out there that have an additional property that's also as convenient as the scaling property, right? It's a very convenient property to have. So basically, if I have two different signals, x1 of t and x2 of t, and I supply the sum of these two to the system, okay? Now, if x1 corresponds to y1, okay, in other words, if I give x1 of t as an input, it produces y1 of t. And if x2 of t produces the output y2 of t, then giving x1 of t plus x2 of t, okay, will produce the signal y1 of t plus y2 of t. It's not hard to see why this can be useful, right? So remember the pulse. The pulse can be expressed as a difference between two unit step functions, right? So those two unit step functions can be your x1 and x2 respectively, right? And y1 of t and y2 of t are the responses to those two different step functions, right? And so you can compose the output much the same as you compose the input in terms of a sum of two things. Now, of course, right, if you were to have a system that goes like this, y of t is d by dt of x of t, right? This system has this property because d by dt of x1 of t plus x2 of t, okay, from basic algebra, and basic calculus, we know that it's equal to d by dt of x1 of t plus d by dt of x2 of t. This is known, right? So for this reason, the simple system that is depicted on your left has this property, and we call this the additive property. Right? Now, what's particularly interesting to us is that there are systems, and they are quite common, that have both of these properties, right? Okay, they have the scaling property and they have the additivity. And you can sort of see how this is useful, right? So if I have two different inputs, x1 and x2, and their corresponding outputs are y1 and y2, then any linear combination of them, for example, c1 times x1 of t, where c1 is a constant, plus c2 x2 of t, where c2 is another constant, okay, this will produce the output, okay, c1 y1 of t plus c2 y2 of t, right? And it's not hard to see how this can be useful. Again, coming back to our rectangle function example, right? Remember, we can write it as a difference between two unit step functions, right? So the output will also be the difference between those two corresponding responses, right? Now these C1 and C2 can be positive, negative, right? Uh, and, and, uh, and also zero, right? In which case this formula always works. Now, systems that have both of these properties are said to be linear, okay? This is what this whole course is about, is linear signals and systems, right? Now, linear systems, signals and systems, are a basic staple of engineering because a very large number of complicated looking signals and complicated looking systems, okay, happen to be linear, okay? Sometimes these things are not linear, in which case it's often advantageous to approximate them by a linear system and then analyze the linear system, right? Now, circuits containing resistors, you know, capacitors and inductors, right? Simple circuits like that, they're all linear. And you know, if we get more complicated kinds of things, right? It can all usually be approximated by a linear model, okay, at least within a reasonable range that represent the operating conditions, right? Now, this property has a name. We call it superposition, okay? Now, superposition is a very, very big deal because whenever we can take advantage of this property, our life is going to be easy, right? We're going to have a whole bunch of formulas and properties that we can take advantage of, okay, in analyzing, specifying, designing, okay, linear types of systems because of the superposition property. Let's consider a very simple example that you see on your left, right? We have a simple two resistor circuit, right? You got a resistor R1, which is 5 ohms, okay, and you got a resistor R2, okay, which is 10 ohms, okay. Now this circuit, okay, has got two sources, right? One of them is a voltage source, okay, V0, which is 45 volts, right? And it's got a current source also, right, which is a 6 amp current source, right? Now, since we know, or at least you can take it on trust for me for now, that resistive circuits are linear, we can take advantage of superposition, right? So you got source 1, source 2. We can compute the responses due to each of these sources individually and then add them up, right? So suppose I'm interested in this current here, okay, I1, right? So suppose this is source 1, and suppose I call this source 2, right? If I1 is the current in this resistor due to source 1, and I2 is this current in this resistor due to source 2, then the total current in this should be I1 plus I2. That's superposition for you, right? So what I can first do is I can basically get rid of this source. The way to get rid of a voltage source is by simply short circuiting it, right? So I got this current source of 6 amps, okay? I got this resistor of 5 ohms, okay? I got a 10 ohm resistor here, and this is short circuit, right? So this 6 amp current is going to get split into these two different currents, okay? And it's going to happen in the inverse ratio of these two resistances, right? In other words, there's a lot more current that's going to flow through this smaller resistance than in this bigger resistance, right? So I1 is going to be given, which is here, I1, okay, is going to be given by 6 amps, okay, which is sort of split in the following proportion, right? 5 divided by, okay, 5 ohms plus 10 ohms, right? So it's 5 divided by 15 is 1/3, and 1/3 times 6 is 2 amperes, right? Now I can also do the same thing, okay, with this source number 1 knocked out, right? And when you knock it out, when you knock out a current source, you basically create an open circuit, which means there's nothing there, right? So you got this 5 ohm resistor here, you got this 10 ohm resistor here, and you got this voltage source, right? 45 volts. So this current, okay, suppose I call this I2, okay, is, now remember the current is going to be flowing this way because this is positive, but if I want to count the current going this way, I'll have to put a minus sign, okay? So the total current is going to be 45 volts divided by 15 ohms, okay? So this is going to be minus 3 amps. So I, which is I1 plus I2, okay, is 2 minus 3 is minus 1 amp, okay? That's the answer. So by taking advantage of superposition, our analysis of this circuit became dramatically simpler, okay? Because we could just selectively disable the sources, calculate the simpler individual responses, and then just add them up, okay? And that works because this system is linear. Now, quite often we are asked to evaluate whether a system is linear or not, right? And in this case, so the straightforward way to do this would be to say, okay, I got two different properties that have to be satisfied. One of them is scaling, and the other one is additivity. Are both of these satisfied, right? That's one way to do it. But if you have any suspicion at all that the system is nonlinear, right, because the formula doesn't look like a linear formula, then it's usually easier to do the opposite, okay? See if the system is nonlinear, right? So for example, if you take the input and you double it, right, but the output doesn't double, then you can immediately with one test say that the system is nonlinear, okay? But on the other hand, to prove that it's linear, you have to show that it conforms to both of these properties, additivity and scaling, right? So a shortcut is sometimes possible, okay, if you kind of think the opposite way. Now, there are a lot of systems that don't change over time. The circuit that we were just playing with, okay, is an example of that. this resistor stays the same, this resistor stays the same, okay? So basically the system response stays the same, right? And this is typical. Once you build a system, okay, it just doesn't change unless it's damaged or it burns out or something, you know, it stays the same. So systems whose response does not vary over time are said to be time invariant, okay? That means they do not vary, right, over time. That's what it means, right? So what does that mean, right? It means that if you had a time axis, right, and if I had a certain input, okay, say x of t, and suppose that produces a certain output, okay, say y of t, right? If I were to scooch this guy a little bit, okay, so suppose I call this, let's start by calling this x1, and suppose x2 of t, okay, is x1 of t minus capital T, where t is some shifting, right, time shift. So I take the same thing and I'm just applying it a little bit later. But since the system is not changing, okay, I should get, okay, the same y1 of t, okay, but shifted by the same amount. And if it's shifted by a different amount, that's bad. If it is shifted in terms of shape or changed in terms of shape, that's bad, right? But if the system is time invariant, then the output will be just delayed by the same number t, right? Such a system in which time shifting the input will shift the output by the same amount and inflict no other change is said to be a time invariant system. Now, time invariant systems are quite common because, you know, like I said, we build things and they stay fixed, you know, for their service lifetime, right? Now, here's a nice example on your left, right? So I have a signal, I move it by t, and the output is also moved by the same amount t, right? So this is a very nice, clean, simple picture whenever that works out. Here are some more examples on your left, okay? So if I take a system such as, okay, y1 of t is 3 times, okay, the second derivative of x of t, right? This system is time invariant because the derivative operation will give the same answer as long as x of t has the same shape. It'll give you the same answer, right? The output waveform will have the same shape. Right? This is also true of simple functions like sine of t, okay, and you know, simple systems like, you know, y3 of t, for example, is x of t plus 2 divided by, okay, x of t minus 1, right? Now these systems are time invariant, right? We'll talk a bit more about how to check for time invariance in the next slide, right? But then let's look at a few examples of systems that are not time invariant, right? These are examples D, E, and F on your right. So what you see there is that the time axis in these, you know, in these functions, okay, has been meddled with, right? So in the first case, the response is actually multiplied by t, right? So that so the actual time matters, right, in shaping the output. So it's not time invariant anymore, right? So it's t times x of t, right? Or if you have something like x of t squared, right, then the actual value of time matters, right? So just shifting the input will not cause the same thing. Now in the third case, x of minus t, it's actually matters even more because the, you know, it's actually flipping it in time, right? It's actually a time reversal. So it's no longer time invariant, right? So let's look at sort of the methodical process for checking when a system is time invariant and when it's not. Okay, so here is the idea, right? So suppose you have a system in which y of t is t times x of t, right? Now we got to be suspicious of this system because the response is actually dependent on the time here, right? So let's just work our way through that, right? So suppose I have an input x1 of t, right? Then this guy is going to produce an output y1 of t, which is given by t times x1 of t, correct? Okay, now suppose that x2 of t is a shifted version of x1 of t, so it's x1 of t minus t, right? What that implies is that y2 of t, okay, is going to be given by t times x2 of t. But x2 of t we know is x1 t minus t, right? Capital T. So t times x1 of t minus t. This is one way of calculating y2, right? Let's see if we can calculate y2 directly, right? In other words, can y2, we can ask the question, is y2 of t given by, okay, y1 of t minus t, right? This is the big question, right? So y1 of t minus t is given by t minus t times x of t minus t, right? So the question is this guy the same as this guy? And it is not. So this system is not time invariant. Okay? So now there is a class of beautiful systems that are not only linear but also time invariant. And our two resistor circuit is a poster child example of that. So systems that exhibit both superposition, which includes additivity and scaling, and time invariance, okay? And these systems are said to be LTI, which means linear time invariant system, okay? So linear time invariant systems and circuits are, of course, prime example of that. I'm talking about simple resistor, capacitor, and inductor type circuits, right? Now this combination of properties, linearity and time invariance, right, allows simple analysis of, pretty complicated systems, right? And we're going to be able to learn all that we need to know in this class, right, this semester. Now, non-LTI systems are going to be much harder to analyze. A system is not LTI is, it could be because it's not linear, okay, with one kind of badness. The other kind of badness is if it's not time invariant. That means the system itself is varying over time, right? So that's another kind of zinger, So again, just like with nonlinear systems, we can often approximate LTI, non-LTI systems with, LTI systems that come close, okay? And we do that so that we are able to analyze it much more easily. Now, let's consider a system that is LTI, okay, which means it's linear and time invariant, okay? And ask the question, what if x of t is equal to the impulse, right? Suppose, okay? Now, the output for this case, okay, which is y of t, okay, suppose we denote that to be h of t. This is going to become very common notation for us, right? So h of t is what we call the impulse response. And it's reasonable because it's a response to an impulse, okay? You give it an impulse and you get an output, and that's why we call it the impulse response. Now this is a special case, right? And you will shortly see why this is such a beautiful and powerful kind of special case, right? What's going to turn out to be the case is that we'll be able to write systems like this. So the impulse response is going to be a complete characterization of an LTI system. So if we know h of t, we know all there is to know about this LTI system. That's powerful, right? And let's see how that plays out. Now, before we get to that, we need to get to know a few more, fundamentals. Okay, so suppose you have a system in which the output is an instantaneous function of the inputs, right? So if you look at the function on your left, right, everything needed to calculate y at a particular time t is available only at that time t. Not before, not after, it doesn't matter, it's only at that time, right? So this is an instant system, right? The output does not depend on past inputs or future inputs or anything like that. Only over the inputs at that point in time t, right? Such a system is said to be memoryless. It has no memory. Okay? Now, systems that do have memory are much more complicated to analyze, right? And for our purposes here, they are going to be outside the scope of this class, right? There's a separate course on dynamic systems that you will be taking probably next semester, okay? And in that case, the output y of t also depends on the past and also possibly future inputs, okay? In the most general case, it can also depend on future inputs, and those are called anticipatory systems because they try to anticipate the future. And that's, a little not so intuitive at this point, so we're not going to worry about that. Okay, so for now we're just going to worry about memoryless systems. Now if you look at an RC circuit, okay, and this is a familiar kind of a circuit, you have a resistor R, okay, and a capacitor C, right? This is ground, and then the input, okay, is x of t, and the output at this terminal is y of t. Okay, this is another way to draw the same circuit, right? So the current through this resistor is I of t, okay, and we want to know what the output of this system is. Okay, we're talking about the output voltage. Now we can call it a circuit, we can also call it a system, right? It's all the same thing, right? So now as a quick recap of circuit theory, right, the voltage across a resistor is simply R times the current through that resistor. Okay. Now similarly, if you have a capacitor, right, the current through this capacitor, okay, suppose we name that I sub C, okay, of t, and if we call the voltage across that to be V of t, right, then C dV by dt equals IC of t, right? Similarly, the voltage across an inductor, okay, is given by L, which is the inductance, okay, times di by dt, L di by dt, right? That's the formula. So the power, of course, in all cases, okay, is the voltage times the current. And this is a signal too, remember? So let's get back to the circuit that we want to analyze, this guy here, okay? We can start to write down the Kirchhoff's Kirchhoff's laws for this circuit, right? So the voltage here plus the voltage here is going to add up to this voltage x of t, right? So x of t equals, okay, r times I of t plus, okay, v of t, right? So this is going to be the voltage across the capacitor, right? And this also happens to be our output, so this is y of t, right? So let's try to, let me rewrite that formula here. So x of t, okay, equals r I of t plus y of t. Okay. Now I of t, as we know, is given by c, okay, dV by dt, and V in our case is the same as the output voltage y, so we can write it as c dy by dt, right? So we can stick this into this formula, okay, and we get x of t equals, okay, r c dy by dt plus y of t. Now this is a differential equation, and we need to, solve this, right? So let's start out by dividing throughout by RC, okay? So we get, and let me flip this equation around a little bit just for convenience. So we get dy by dt, and divide this by RC, so this becomes a 1, okay? Plus, okay, 1 over RC, y of t, of course there's a t here, okay? Equals 1 over RC, okay, x of t. Now, what I'm interested in is the special case when x of t is an impulse function, d of t, right? This is what I'm interested in. So I can rewrite the formula, okay, as dy by dt plus 1 over RC y equals, okay, 1 over RC times delta of t. Now, a bit of review is in order at this point in terms of differential equations. So in order to solve a differential equation like this, okay, we need to do something, okay, so that we can integrate the left-hand side, right? So you might remember from calculus that if you have two functions, u and v, right, and they were multiplied together, right? Suppose I take d by, dt of this product, u and v, right? It's u dv by dt plus, right, v du by dt, right? So if we somehow magically can identify a product of this type, okay, we can integrate what's on the left hand side. Now this can be done by multiplying throughout by what is known as the integrating factor, right? The integrating factor is simply e to the this guy integrated, right? So if you take so the integrating factor, okay, in this case is e to the 1 over RC, okay, integrated over dt, right? And if we were to apply that, okay, let's see what we get, right? So we get, this paper is messed up. So let's see what we get. So we have dy by dt, okay, times e to the t over RC, okay, plus 1 over RC, e to the t over RC, okay, times y of t, okay. On the right hand side we get 1 over RC delta of t e to the t over RC, right? Now the left hand side, okay, is basically d by dt of a product of two things, y, okay. So this is given by, 1 over RC, okay, e to the t over RC, okay, delta of t. This is the right hand side. So we can now integrate both sides, okay. So y times e to the t over RC is given by integral from 0 to t, okay, 1 over RC e to the t over RC delta of t. Now in this case, we can't start, we have to include, the range where, the region of the t-axis where delta lives. So we have to actually start, a wee bit to the left of the axis, right? So it's 0 minus 2t, right? And we can now use the sifting property or the snapshot property of the impulse, right? So the right hand side, okay, is given by 1 over RC, which comes outside, okay? This comes outside, okay? And T over RC gets sampled at the time where delta of T is non-zero. And that only happens, okay, when T is 0. So E raised to 0 is just 1. So it's just 1 over RC, okay? And this function only lives to the right of the axis. So we have to actually multiply that by the unit step, right? So y of t, if I were to take e to the t over RC to the right hand side, I get 1 over RC e to the minus t over RC u of t. Okay, this is the impulse response of this system. Okay, so we just now calculated the impulse response, okay, of this RC circuit, right? So basically our impulse response, denoted h of t, is 1 over RC, okay, e to the minus t over RC, okay, u t. Okay. And so what we want to do next is replace the input with a unit step instead. So let's try to figure out the unit step response of the same circuit. So the circuit is still the same, okay? So the basic equation we have to solve is still the same as before, okay? So this is the equation that we have on the top left, which is integral from 0 minus to t 1 over RC e to the tau over RC, okay, delta of tau d tau, right? Except we're going to replace this, okay, with unit step. That's what we're going to do, right? So let's do that. So we get y of t e to the t over RC equals, okay, 1 over RC e to the tau over RC, okay, u of tau d tau, okay. Now introducing a unit step here basically multiplies this stuff with a 0, by the way there should be a minus, okay, whenever tau is negative, and multiplies everything positive by 1. That's all it does. So it doesn't really change much, okay. So this integral, by the way, let me go to the next page, okay. So this integral is simply given by 1 over RC, I can take this guy outside, integral from 0 minus to t e to the tau over RC, okay, d tau, okay, and so this is 1 over RC, okay, e to the tau over RC divided by, okay, 1 over RC, okay, where this tau goes from 0 minus to t. Okay. So I can pretty much cancel this guy, goes away. Okay. So this is equal to e to the t over RC minus, when you stick in 0 minus here, okay, it's essentially 0. E to the 0 is just a 1, so you just get a 1. Okay. So y of t in this case, okay, can be solved. Oh, by the way, this whole thing can be multiplied by u of t because all of this applies only to the right hand side of the axis. Okay. So y of t is e to the minus t over RC. I'm basically taking this term to the other side, okay, times e to the t over RC minus 1 u of t, which is basically 1 minus e to the minus t over RC times u of t. So this is the step response, okay, of the same circuit. So it might be fun to just plot these functions, okay. So the step response of this RC circuit kind of looks like this, right, like that. Whereas the impulse response, so this is like y step versus t, okay. Whereas the impulse response, okay, h is like that, and the impulse response is labeled h of t. Got that? Okay, and it sort of makes sense, you know. Basically, the capacitor is charging up. When you apply a step function, it's like you turned on the switch, and the capacitor starts to charge up, okay, until it reaches the same voltage as the input source, right? And then in this case, right, when you apply an impulse, basically it charges the capacitor briefly and it starts to discharge, and that's what it looks like, right? So this is like a charging of the capacitor, okay, and this is like a discharge following a brief, you know, charging. So how do they relate, right? So one of the things that we do know, okay, is that the delta function is d by dt of the unit step function, remember? So the step function goes like this, and if you differentiate that, you get the delta function, right? So this is delta of t, this is u of t, right? So since we know that this is a linear, you know, actually also time invariant operator, right? What would happen if I were to, you know, differentiate the response to the step, right? So if I take d by dt of y step of t, right, which is d by dt of 1 minus e to the minus t over RC, okay, u of t, right? What do I get? So basically, if you were to go through the process of differentiating this, right, and you know, you can sort of look through the gory details on the left-hand side, okay, the final answer turns out to be relatively clean, okay, e to the minus t over RC u of t. this is the same as h of t, right? So this is a very satisfying result, which tells us that you can differentiate the step response to get the impulse response. And this observation also has some practical implications. So I realize that we haven't talked about convolutions yet, but so think of this particular slide as a bit of a preview of what's to come, but the reverse also works. In other words, if you know the impulse response of a system, right, you can use that to calculate the response to a step, right? So if you know the impulse response, you can calculate the step response. In fact, you can calculate the response to anything else, knowing the impulse response. Such is the power of the impulse response, right? And the tool that gets us to do that is what is called the convolution integral. Okay. And what you see on the left is the convolution integral in action. So we're going to talk about the convolution integral in the next lecture. But for now, I just want you to pay attention to the final result, right? So if you look at the bottom line, if you look at the y step, right, of t, at the bottom right, it turns out to be 1 minus e to the minus t over rc. Okay, exactly what we expect, right? So we're going to talk more about the convolution next time. Now this stuff, if you understand it clearly the first time, okay, you're just going to get it. It's going to be easy, right? But if you don't get it, and if you confuse yourself, you will not get it for for a long time. So the convolution is going to be an important theorem. So do come prepared to the next class, lecture 5. Okay, so let's move ahead. So this number RC that you see out here is called the time constant. Okay, and we denote that tau C. Okay, so if you have a big fat capacitor, the time constant is going to be very long, and if you have a tiny capacitor, the time constant is going to be very short. And at the same time, if you have even a small capacitor but a very high resistance, so the capacitor charges very slowly, then you're going to have a large time constant, right? Therefore, it makes sense that the product of R and C defines the time constant. Okay? If the capacitor is big, it charges slowly. If the resistor is very big, it also charges the capacitor slowly. Okay? Let's move on. Now, if you go into the lab, right, what you're going to find are instruments that kind of look like this, right? And one of the instrument that you see on the top right, okay, is called a function generator, right? It's got a bunch of buttons in front. If you look carefully, okay, you'll find buttons that look like this, okay? If you press that button, it's going to generate a sinusoid. There's going to be a button that looks like that. If you press that, it's going to create a pulse and things like that, right? Now, on the bottom right, you see another instrument, and this one is called an oscilloscope, right? Basically, it's saying that the signals are some kind of oscillations, and scope means to see, right? So it allows you to see these oscillations. And what you see on the display is a nice, beautiful pulse function being displayed, right? It's very nice and clean, right? So now a lot of the time, okay, like that an impulse response is often hard to, an impulse is hard to generate. So trying to observe its impulse response, a circuit's impulse response, can be hard, right? So what we're going to do is that we're going to try and generate very narrow pulses, right? Like that. So if you generate a very narrow pulse, it's a decent approximation to an impulse, and it gives us, and the response of the circuit to that, okay, gives us a bit of an idea as to what we should expect, right? Now, at the same time, what you can also do is that you can give a unit step-like response, which means a very broad pulse, right? And see how the circuit responds to this step, right? And from that, you can deduce the impulse response by differentiating it, right? So these oscilloscopes are very, very useful things, and so are signal generators, right? A signal generator can produce a controlled, signal. And if you look at the buttons on that, one of them is actually a ramp, right? The fourth button, okay, so this is a 1, 2, 3, 4. The fourth button here is actually a ramp, okay? So these are pretty cool things. So once you get to the lab, you're going to have a fun time playing with some of these instruments. Okay. So when I spoke about, you know, trying to approximate delta functions and unit step functions, right? There are a couple of details that I left out, so let's talk about that a little bit, right? So the practical question is just how wide does this pulse need to be so that this part of the pulse, right, is a decent approximation to a unit step, right? And at the same thing, how narrow should this guy be relative to this so that this is a decent approximation to a delta function. So let's look at that in a little bit more detail in the next example. Okay, so here is an RC circuit that, the good old familiar stuff. You got a resistor, you got a capacitor, it's ground, okay, and you got the input, x of t, okay, specified relative to the ground, and then you got the output, y of t, again specified relative to the ground, and you got the capacitor here, right? So suppose the RC time constant, okay, is 2 seconds, okay. In that case, suppose I were to have a pulse, okay, the input pulse that's pretty wide, okay, it's like 5 seconds. So the width of this pulse in this case is sort of the same order of magnitude, okay. It's not like a tenth of this or anything like that. So the same order of magnitude as the time constant, right? In this case, if you look at the output, okay, this is plotted on your left, okay, and what you sort of see is that the signal kind of rises nicely, okay, and then sort of falls off, okay, after 5 seconds. So this is input, and this is the output, y of t, okay, y pulse of t basically. And this is time, and this whole axis is of course the time. So now let's see what happens when you shorten the pulse a little bit. Okay, let's go to the next slide. So now the tau c, or the RC value, okay, it is still the 2 seconds. We're keeping the circuit the same, right? But what we're doing is that we're changing the width of the pulse, okay, and our input now, okay, is going to be kind of like this. It's going to be a 0.05 seconds. Okay, so this width here is 0.05 seconds. Okay, now clearly this, okay, is much smaller than tau c, right? So if you look at the output, okay, which is plotted on your left, okay, as the blue line, you'll sort of see that the signal rises super fast. It's a very fast time constant, and then it starts to fall off, right? And by the time you get to about, say, 5 or 6 seconds, okay, the signal is pretty negligible, right? So by the time you certainly get to about 10 seconds, this guy is pretty much gone, right? Now let's see, and so this is not a bad approximation to a delta function, okay? Now you should compare this with the theoretical one, right, for a delta function. So the um, the response to the delta function, okay, is h of t, right? And this is equal to 1 over RC e to the minus t over RC u of t. Remember this? So this is looking quite close to that. Now let's take it, kick it up one more notch. Okay, now this time the RC time constant is still the same, but now the new tau c is 0.01 second. It's like 1/5 of the previous one. It's a very, very narrow pulse, and you can sort of see that the approximation gets even better. Now importantly, if you pay attention to the peak of this pulse, right? So in this case, with the 0.01 seconds, the peak of the pulse is close to 0.5, which is like the theoretical. It's like 0.499, okay? It's a decent approximation. Now, previously, it was like 0.494, and then before that, okay, it only came up to about 0.2, right? So the bottom line is that the width of the pulse, okay, relative to tau c is what matters. And it shows up in the formula, right? So if you look at the formula, right, you can sort of see that the time is being divided by tau c, or the RC constant, and so it's the ratio that matters, right? So to summarize, if we go back to our laboratory setup, right, then if I want to approximate a delta function, right, I want to make sure that the um, the interval between the delta functions, okay, is of the order of tau c, probably more than that, right? Maybe 5x, okay, should be okay. And then this guy, the width of this pulse, okay, should be much lesser than tau c. If it's 1/10, you're already, it's a pretty decent approximation. If it's 100th, wow, it's golden, okay? It's plenty good enough. So I hope that gives you a bit of intuition in terms of how to make circuit type measurements. Now, the other thing to keep in mind is that the delta function, okay, is a harder thing to produce. But on the other hand, if you look at the step function, okay, that's easier to generate. It's a more well-behaved thing. So if you can find the step response and then differentiate that in order to figure out what the impulse response should be. Okay. In fact, if you're in the lab, try it both ways and make sure that the answers are reasonably consistent. And the accuracy of the approximation depends on the ratio. Okay, so a couple more concepts before we wrap up. So there are systems like the one pictured here. Okay, suppose I had a system that has the following input-output relationship, right? It's sine of x of t divided by x squared of t plus 1. Or another example is just say y of t is, say, 2 times x of t, right? These kinds of systems are such that the output at any point in time depends on the instantaneous output at that time, right? So it doesn't depend on what happened before, right? You come in tomorrow, you get the same answer, right? So these kinds of systems are known as memoryless systems because they don't have any memory. Okay. Now, when a system does have some memory, okay, it becomes a little bit more complicated to analyze, right? Now, the RC circuit that we just analyzed, it remembers the past input to some extent, right? It depends. It depends on when you deliver the pulse, for example, right? Whereas the memoryless systems are much easier. Now, if a system does have memory, okay, or in other words, non-memoryless systems are known as dynamic systems. Okay, and by and large, the subject of dynamic systems is outside the scope of ECE 3337. Okay, so but happily we have a separate course for dynamic systems, and I hope you sign up for that. Maybe next semester or something like that. Right? So for a dynamic system, the output depends on past inputs. Now, for certain kinds of dynamic systems, it could also depend on future inputs. In other words, they can anticipate the future. I know that sounds a little crazy, but if you think about it, right, if you think about a signal that's multidimensional, you remember we talked about an image as being a multidimensional signal, right? And if you think about the signal in X and Y, right, one can have systems that are, that can be anticipated and can be quite meaningful. Okay, so it's not as bad as it sounds. Anyway, this is the stuff for another semester. So to summarize, linear time invariant systems are both linear and time invariant. This combination of properties is magical, right? It's enabling. So as an engineer, okay, we seek out linear time invariant system type models. And when these properties are met, our life is so much easier. We can build a system, know exactly how it will behave, right? We can write down formulas that we understand to the hilt, okay? And happily, the world is full of such systems, and they are pervasive in that sense. They're also important because a lot of important systems happen to be linear time invariant. Okay, and so expect to work with linear time invariant systems for a long time, long after this course is done, right? As you go about practicing, as you in your career, right? You will encounter these systems quite a bit. Today we also learned to analyze a very simple LTI system, which was an RC circuit, right? And we did that in order to learn some important lessons. Some of the lessons that we learned was that we can calculate from first principles using our knowledge of circuit theory, right? So given our good old RC circuit, we could figure out what its impulse response was, right? So we give it an impulse, we know the output, and we call it h of t. Then we also, from first principles, right, we integrated the formula to figure out what the output should be, okay, for a unit step function. And the thing is, then we sort of understood the relationship between these two guys, right? And that reflects the relationship between these two guys, right? If you integrate the delta function, you get the unit step function. If you integrate this, you'll get this. Or if you differentiate this, you'll get this, right? So sort of it works very nicely, right? But going from the delta function to the response to the step function, right? In other words, knowing the impulse response, which is h of t, finding the step response, will take a bit more understanding. It's an integral, we understand that, but that integral is going to be a special one, right? And we sort of took a preview of that today, but in the next lecture, we're going to really talk about that, and that's going to be called the convolution integral, right? And the convolution integral is a fundamental concept in electrical engineering, okay? It's also a sort of a signature, um, formula that we're going to use over and over again for linear time invariant systems, right? And we're going to talk about that in the next lecture. So for the next lecture, I'd like you to work through the textbook examples in sections 1.4.4 and 1.5, right? Basically, the answer is there in the book. Try to work these problems on your own and see if you get the same answer as the authors did. All right, if you have any questions, ask me. And then for the next lecture, I want you to read section 2.3. This is important because this concept of the convolution integral is actually remarkably simple to understand if you're prepared for it. Okay, if you're prepared for the class, you're going to just get it. Otherwise, pardon the pun, it's going to seem all convoluted. Okay, so see you in the next class.